My talk is going to give a very brief history of Martian meteorite chronology, as much as I can fit into the next 18 to 20 minutes. But I have also provided, well, there's my email if you have any questions. I have also provided a reference list at the end with links so that once you have this, we can make this presentation available. Once you have that, you'll be able to go to the original sources, as it were. So the front page here is to remind us that we're looking at meteorites, including some very significant ones, Elephant Moraine 7801 in the lower right there. And it is really about Mars in general, the history of Mars, how it relates to the Earth, how the two planets compare. So the big picture is worth keeping in mind here as well. Now, some of the challenges in working with these particular rocks, they're relatively rare meteorites. Out of the 60,000 or so that we have, there's only about 160, and the recovery of those has really only, of the majority of those, has really only been the last 10 to 20 years. The majority are relatively fine-grained basaltic rocks, with some exceptions, but that makes it challenging for mineral separation. Tim's work, as you'll see, is the majority of the work that has been done. It's not the type of thing that is sort of readily set up and done, requiring low blanks and that sort of thing. All have been shocked up to tens of gigapascals. There's a range of them among the Martian meteorites, but some of those effects of shock include the formation of meskelnite, which you can see in the lower panel here, where in this photomicrograph and plane polarized light in the center, you can see that you have these grains that for all intents and purposes look like plagioclase, but when you cross the polars, they are isotropic. And so they are a diaplectic glass now with a feldspar composition. They basically have lost their crystal structure during shock compression. Planar deformation features is another effect. Melt veins and melt pockets is also another effect. Now, that being said, we do have, I think, quite a good understanding of those shock features and how to account for them in the work that is done to try to determine the ages of these meteorites, but it is an important factor to keep in mind. Another thing, a little bit of a sort of brief history, is that these meteorites were originally known as the SNC meteorites after the Shrigati, Nakhla, and Chassigny meteorite falls in the dates shown here. And then other meteorites that fell, for example, Zagami, or were found, for example, in the Antarctic, these ones, were grouped into those on the basis of their petrography. And so we had these SNC meteorites, and we still use those terms. We've inherited those terms. So you'll see the term Shrigotite, Nakhlite, and Chassignite in this talk. But we didn't know where they were from. They were all oddballs. They are all thought to be, at least based on their petrography, to be from a differentiated asteroid, for example. But the parent body of the planet from which they came was really unknown until McSween and Stolper suggested in 1980 that they could be from Mars, and then Bogart and Johnson showed that there was atmosphere trapped in these meteorites that matched the composition of the Martian atmosphere as determined from the Viking landers in the 1970s. And we now have an understanding of how these rocks get delivered to the Earth. An impact occurs on the surface of Mars, and even the detail now tells us that of the modeling tells us that an annular ring around the point of impact, those rocks at the surface get accelerated fast enough to leave Mars gravity and then make their way to the Earth. Now, keep this process in mind because it helps to explain this. The violence of this process helps to explain some of the particular distribution of ages and features of these meteorites. But spoiler alert, they don't have, they're not sedimentary, they don't have green slime on them. Okay, if we look at one of the very early studies of these meteorites, now keep in mind Bogart and Johnson had suggested they're from Mars with the trapped gases in 1983. In 86, this paper by Chen and Wasserberg was published on these three shergottites using the uranium lead system. And interestingly, they determined, as you can see on this 206, 238 diagram on the left, you can see that they were able to regress lines through some of the separates for Zagami, showing an age of about 230 million years, for Shigati 200, and EETA 7901 about 150 million years. But they noted that things like the mescalinite, the plagioclase don't plot on the lines. They also noted that, for example, over here on the right, that the intersects of the Concordia were at about 4.5 billion years and about 170 million. And so despite the sort of relative consistency of these ages as being around 200 million years, they nevertheless concluded that the timing of 200 million was the timing of resetting by impact, forming the mescalinite, for example, and that the actual formation age, the crystallization age, was 4.5 billion. That is consistent with, excuse me, with an old sort of early formed and differentiated parent body. In the very same volume, the following paper is by John Jones, who considered different scenarios based on the data, including uranium, thorium, lead, but also rubidium, strontium, and samarium, neodymium. Consider different scenarios, such as, okay, they all formed at 4.5, but were reset, or they formed at different times, or they, or basically trying to understand why, to rationalize why, in particular, the three systems which agree, as you can see here, EETA 7901 with this RBSR determination is consistent in terms of its age, about 170, 180 million years. As well as the preservation of disequilibria and compositional zoning, he concluded that the shergottites are indeed 200 million years old in terms of their crystallization age. Meanwhile, the nakhlites and chassigny at the time had been, ages had been determined on them about 1300 million years, and they're lower shocked as well. And so that age was fairly consistent. And he argued that basically these relatively younger ages are indeed consistent with coming from a planet such as Mars, where you have enough internal heating to continue up until relatively recently. In 1997, Borgenol was working on QUE 94201. It was a relatively recently recovered Martian meteorite from Antarctica at the time, and determined an age for that. And also noted, though, that when you plot up the whole rock, rubidium strontium isotopic composition on a diagram like this, that QUE and ETA and Zagami and Shigati, in fact, the majority of the Martian meteorites known at the time fall on this 4.5 billion year reference line. I'll come back to how they interpreted that, but they nevertheless found that the ages of these rocks were still around 175 in these cases and 330 million years for QUE 94201. But they had these very different positions on this line. So this is schematic, this slope here showing a shallower slope for Zagami, showing that mineral separation within Zagami and isotopic composition of those separates is consistent with an age of 175 million years, yet they plot in a whole rock sense on this 4.5 billion year line. So we'll come back to the 4.5 billion year thing, but it does still suggest that these rocks are indeed young. And then revisiting uranium lead, Lars Borg and colleagues in 2005 published this paper where they again looked at Zagami and looked at the same whole rock mineral and leachate fractions, and they did uranium lead, rubidium strontium, and samarium neodymium on those same fractions. And they got good concordance between rubidium strontium and samarium neodymium, as you can see here, and lead 238, 206. The uranium lead, they got 156 million years, and they compared that to the 230 million year age or determination of Chen and Wasserberg. And this is as well as and they also noted that in 235-207, they have really no age significance. This 360 plus or minus 220 million years is really uncertain, and it's really just done selecting particular residues. So they didn't discuss the presence of a radiogenic contaminant that disturbs the uranium lead system. And they said they considered how it could be terrestrial, of course, from curation and handling or saw cutting, that processing, that sort of thing. But they also said perhaps it's Martian. Perhaps there's a Martian contaminant that has made its way into these rocks that is disturbing the uranium lead system. Meanwhile, Audrey Bouvier and colleagues published a paper around the same time where they looked at shergottites as well using the lead-lead system. This is with a series of leachates residues and with a series of leaching of the mineral separates, and plotted them up along with the Chen and Wasserberg data, and showed that they plot very nicely on a line that has an age of 4.05 billion years. And they argued that based on the fact that the surface of Mars is relatively old, that is, the majority of the surface is quite old as 4 billion by some estimates, that it made more sense that these rocks would be 4 billion years old and they've been reset. So they kind of brought up again this original idea that they are old and have been reset at much more recent times. Okay, then within the last 10 years, there's a couple other studies that took advantage of the accessory minerals, in particular badlyite. And so this is a study by Zhou et al. That I basically led. I had done a sabbatical at the Smithsonian in 2010, 2011, and part of that, the main purpose was to actually go through Martian meteorites, shergottites in particular, and map out where badlyite occurs. And you can see some occurrences here. Spent a lot of time finding hundreds of grains in Zagami alone, and then we use that information with my colleagues in Beijing using the IMS 1280 iMicroprobe. And here you can see 18 data points, and on this modified Terra-Wasserberg Concordia diagram, and the lower intercept gives an age of 185 plus or minus 9 million years. And so the advantage of badlyite is, like zircon, it excludes common lead when it crystallizes, and it's a really good capture, and it sees through most shock, and is able to then, so this is further support for the crystallization age being young. And we published this table, and it shows that with a whole bunch of different systems, including samarium, neodymium, lutetium, hafnium, which was obtained by Bouvier et al. In that same study for Zagami, argon, which has some complications because of other atmospheric gas being, or other sort of complications with the argon system. But for the most part, all of these systems are in the same ballpark of about 200 million years. So with the exception of the lead age of 4 billion. And then additional insights were gained by this study, which is a really elegant study by Des Moser, James Darling, and others, where they looked at badlyite and demonstrated, and we'll hear more about this in this workshop, but determined that the dated badlyites retain many characteristics of primary igneous badlyite. The oldest measured grains retain igneous twinning and zonation, and they determine they're consistent with the igneous event that formed the rock at about 200 million years. That this is a much higher shocked shergottite than Zagami, for example, and shock resetting has caused these ages to trend towards much younger. And also there's zircon that has formed as a result of the interaction between the badlyite and the shock melt. And so this sort of resetting indicates is consistent with the shock occurring at the time of launch from Mars to the Earth, and they get a maximum age of that of 22 million years. And in fact, the cosmic ray exposure age for this rock is about 4 million years. So it's consistent with the shock partially resetting the badlyite in particular locations within the rock at that time. They furthermore, with the lead systematics as shown in the inset here, show that the radiogenic component in the sample is, while the radiogenic component in the sample is young, the unradiogenic mineral analyses record mixing of distinct common lead components. And that's further, so that follows the suggestions of Borgenol, and is further strengthened by subsequent work by Bellucci et al. in 2016, including the lead paradox resolved. So we think that the lead paradox is largely resolved, that the 4 billion year age by Bouvier et al. is thought to be essentially an artifact of mixing between the intrinsic compositions of the minerals and some kind of even Martian contaminant that has permeated the sample. Okay, so now we have these, and this is showing you now sort of what how the distribution of different types of Martian meteorites by number. So this is, so the 82% is by number, and you can see the vast majority of these sturgatites, which have ages now ranging from about 165 to 700 million years. We also have nachtlites and chassignites, which all have ages around 1300 million years and may be related to each other. There are two that have ages of 2400 million years. These are so-called augite-rich sturgatites. They have different characteristics though that may or may not mean they're related to these the classical sturgatites. We have Allen Hills 84001. There's only one of those. That's an orthoperoxenite with an age of 4100 million years. And then we have NWA 7034, which is a very interesting recovery in recent years, which is a breccia. And it has zircon-bearing clasts that have ages of 4300 million or more. And the assembly age is thought to be around 1300, 1500 million years. So that's where we are at. And what we can infer from this is that there's a bias in the sampling. That violet process that I mentioned preferentially launches younger igneous rocks more competent rocks off the surface of Mars and delivers them to the Earth, which is the reason why the sturgatites are predominant and why we have such a bias towards young age rocks in the collection. But what about this? What about this 4.5 billion year reference line, and indeed any sort of old age that we get from this? Well, this can be explained through planetary differentiation. In particular, RBSR can be considered in terms of whole rock mixing, and essentially the mantle of Mars or components within Mars that have been separated for 4.5 billion years. Such that you have these different components, depleted, sort of intermediate and evolved components today that then plot along this line. And this is an interesting and I think unique thing about sturgatites in particular is that you can plot them up on a diagram like this. So this is essentially reflecting this is the epsilon 143 neodymium on the y-axis and the rubidium strontium 8786 on the x-axis. And you have these groupings, and you have long-term incompatible element enriched rocks shown down here in the blue, and you have long-term incompatible element depleted rocks shown up here in the red, and you have intermediate ones. And in fact, their rare earth element patterns, their whole rock rare earth element patterns are consistent with this, where these ones here have a depletion in the light rare earth elements. So the lanthanum terbium ratio is low. The enriched ones really have a flat rare earth element pattern, and then you have intermediate ones. And this seems to continue to hold for nearly all of the sturgatites. And if we interpret these as being separation of components within the mantle, then they probably formed during crystallization of a magma ocean. And we are at 4.5 billion years ago, and we're variably tapping these sources that are either depleted, enriched, maybe containing trapped liquid from the last dregs of crystallization of the magma ocean, or somewhere in between to get the intermediate source. And the other important thing about this is that there's no petrographic association between depleted, intermediate, and enriched. So these are interesting and important sort of implications. And to kind of summarize then, we have with this diagram, this is from a paper by Arya Udry, myself, and others, a review paper that we published last year on what we learned about Martian meteorites in the past 5 years. You can see the timescale for Mars up here, as determined from orbital observations, remotely sensed geology of Mars, and the approximate ages based on extension of the lunar timescale, cratering timescale to Mars. And then on that, we have these shergottites. So you can see, again, this bias towards these much younger, mid to late Amazonian age rocks, with the exception of this 2.4 billion year grouping, and Allen Hills 84001, Knocklite Chassagnites here, and the class within NWA 7034. But the other interesting, so there's some gaps here, but the other interesting thing is because these rocks, these young rocks, record ancient mantle reservoirs or mantle components, we can say something about those source ages, and those source ages are ancient. They formed within the first 100 million years of Mars history. And really this fits with the idea that Mars is poorly convecting, and we haven't really recycled anything into the mantle. That these have been separate for that length of time. And so we've established these mantle sources at 4.5 billion years ago, and then they've been tapped by melting at much more recent times. But we could also say something, we can even constrain the timing of accretion, core formation, crystallization of this magma ocean, and the formation of the crust. So they have really great, useful information and valuable information, however, there's this bias in sampling, and so we've got gaps in the chronology, and we cannot link these rocks to specific units on Mars, having crater retention ages, and that's something we'll hear about later and maybe discuss later. So all of this informs, in fact, what we want in terms of samples that we bring back from Mars. You know, we're going to want something that is in the Hesperian to Noachian, or that's in this gap that we're missing in the Martian meteorite suite. And of course, it's important that we have the context for those samples so that we can determine how they fit and whether we can get an absolute pinning point to nail down this Martian timescale, which has a lot of uncertainties. So that is it for the brief summary, brief history. And there's the reference list, which I can, like I said, we'll make this available so you can follow those links. And yeah, let me know if you have any questions. I'll stop sharing now and we can open it up if anybody has any questions or comments before we move on to the next talk.